Hello, everybody. Welcome back to class. First class of the week. Looks like there's only a few of you here today. Hopefully a few more trickle in before class starts. Let's make sure my camera is good. Navik knows the drill. Smash the like button. Sip. Excellent. Well, say hi when you get here so I can know who's here today. Molly's in the chat. Cruz, good to see you. Good morning, Emma. Good morning, Shutong. Glad you're here. All right, well, it's 9 o'clock. So that means it's time for the simultaneous sip. So if you have your coffee or water or whatever, and you have it ready, please join me. All right, yeah, let me know in the chat, of course, if you joined in on the sip. And, let me know if you didn't join in on the sip. Just, it's okay if you don't. But yeah, so we'll get started in a second. As a reminder, you have a homework due tonight. Good morning, Cal. You have a homework due tonight, so try to get that in before, I think it's due at 11:59 Eastern. So plan on finishing it well before that. So if you have any technological issues, you could just upload it. Okay. So, yeah, before we move on to the new stuff, let's just kind of recall a definition that we talked about at the end of last class. I know it was a while ago. So a set U1 through, let's say, UP is an orthonormal set if what were the what conditions have to hold for a set to be orthonormal? There's two conditions. We didn't list them in two conditions when we wrote out the definition, but we can kind of summarize it in two conditions. The two conditions are ui dotted with uj is equal to something if I is not equal to j. So what is that something? And the other condition was the length of ui is equal to something else for all I. So what was the condition for a set? If a set was orthonormal, if you took the dot product of two vectors, what should you end up with? So fill in these blanks. Yeah, we want 0 if you take the dot product of just two vectors that aren't the same. That means they're orthogonal. And then what did the normal part mean? Right, because if it was an orthogonal set, we would only have this first condition. And in an orthonormal set, the length of each vector is what? Well, it's in your notes somewhere, I'm sure. The length of each vector is 1. Okay, so if you have an orthonormal set, the dot product of two vectors that aren't the same. It's all right, William. I'm glad you're here. The dot product of two vectors that are not the same is 0, and then the length of any vector is 1. Okay. So let's state a theorem about orthonormal sets. Yeah, good, Maddie. The theorem says an m by n matrix, which we'll call U, has orthonormal columns if and only if U transpose times U is equal to the identity matrix. Yeah, Shutong, another way to write what we wrote here. Yeah, we would say, well, the magnitude of U sub I is the square root of UI dot UI, which is just 1 in our case. Okay, so our theorem says an m by n matrix U has orthonormal columns if and only if U transpose U is equal to the identity matrix. Okay, and this should follow immediately if you write out what the multiplication is. And we'll just kind of see it by an example eventually. But basically, if you take a row of U transpose, that's the same thing as a column of U, and you multiply it to one of the columns of U, well, it's going to be 0 unless it's the same entry, then it's going to be 1. So you'll have 1s down the main diagonal and 0 everywhere else. So another theorem. So if we have an m by n matrix U, with orthonormal columns, okay, so we have some m by n matrix with orthonormal columns, and let x and y be an Rn. Then the following hold. The magnitude of U times x is equal to the magnitude of x. Okay, so this first part says if you multiply, this doesn't look very good. If you multiply by the matrix U to x, and we have orthonormal columns, the magnitude doesn't change at all. Okay, the second part says the dot product of Ux and Uy is equal to the dot product of x and y. Okay, so multiplication by u preserves the dot product. And then last, well, this is basically the same thing as b, it's just a special case of b. Ux dot uy equals 0 if and only if x and y are orthogonal. So what does this theorem say? It says, basically, it says the linear map which sends x to ux preserves length and it preserves orthogonality. Okay, so I'll give you a second to catch up with writing down this theorem, but we'll get to an example. Are there any questions before we move on to an example? All right, well, I'll write out the example. If you have any questions, feel free to ask them. Okay, so it's so we'll let u be the vector. Let u be the matrix 1 over root 2, 1 over root 2, 0, 2/3, negative 2/3, 1/3, and x be the vector square root of 2, 3. Okay, so the example is show that u has orthonormal columns, and then verify part A of the theorem. Okay, so I'll give you a few minutes to work this out. Does somebody in the chat want to suggest how they're going to show that u has orthonormal columns? And if you're unsure, maybe just put a question mark or something, and then hopefully somebody could explain that to you. If not, I'll tell you in a second. And so how are we going to show that u has orthonormal columns? Yeah, exactly, Shitong. So we want to show that U transpose times U is the identity matrix. All right, so let's just do the matrix multiplication. U transpose, remember U transpose, you just take U and flip it, switch the rows and columns. So if we show U transpose times U is the identity matrix, this theorem shows that we have orthonormal columns. I guess we could also do what Molly said. Check that the dot product of the two columns is 0, and they each have length 1. Yeah, that works too. Okay, well, I'll start working it out. So to show that U has orthonormal columns, let's do the matrix multiplication, U transpose times U, and see if we get the identity matrix. Okay, so this is U transpose times U. All right, can I get a thumbs up in the chat if you remembered, or if you at least got this far? And now we're going to do this matrix multiplication. Top row times the first column would be 1/2 plus 1/2 plus 0, which is 1. Two over 3 root 2 minus 2 over 3 root 2 plus 0 is 0. 2 over 3 root 2 minus 2 over 3 root 2 plus 0 is 0. Four ninths plus 4 ninths plus 1 ninth is 9 ninths, which is 1. Okay, so we just showed that U transpose times U gives us the identity matrix. So by our theorem, that tells us that U has orthonormal columns. Okay, and now the second part of the question is verify that the length of ux is equal to the length of x. So let's find the vector ux. So we take the matrix U times the vector X and just multiply it out. It's 1 plus 2 is 3. 1 minus 2 is minus 1. And 0 plus 1 is 1. The magnitude, or the length of ux, is equal to the square root of 9 plus 1 plus 1, which is the square root of 11. The magnitude of x is equal to the square, this is x here, the square root of 2 plus 9, which is also equal to the square root of 11. So we verified it. The theorem holds in this particular case. Any thoughts or questions about the example we just did? I'll give you a second to write this down and ask any questions you have. You know, I'd love some sort of thumbs up or something if we're good to move on. Thank you, Shutong, for the response. Okay. Ooh, 2 of them. So we'll state a theorem. The theorem says if U is a square matrix, if U is a square matrix with orthonormal columns, then U inverse is equal to the transpose of U. Okay, and so let's just give a quick sketch of why this is true. Why is it the case that if U is a square matrix with orthonormal columns, then the inverse of U is equal to U transpose? Well, let's think. U has orthonormal columns. So our previous theorem, or the theorem two theorems ago, okay, so this is from 2 theorems ago. This is exactly what it means to be an inverse. Right, so there's nothing else. There's nothing new to this. This is just a special case of the theorem before. Right, so what does it mean to be an inverse? If you're a square, right, you can only have an inverse if you're a square matrix. We have a square matrix. The inverse is the matrix where if you multiply the two matrices together, you get the identity matrix. And that's exactly what we have here. So this is just a special case of the previous theorem. Okay, well, if there aren't any more questions, we can move on to section 6.3. Which is orthogonal projections. So we talked last class or 2 classes ago about how to project a vector onto a line. But what we're going to talk about in this section is in the more general sense. How do we project a vector onto a subspace? Not a one-dimensional subspace, but a higher dimensional subspace. Okay, so we'll start by kind of sketching out what we're dealing with. And then we'll do an example, hopefully. So given a vector y, and a subspace W in Rn. So, last section we used L for a line. Here we're going to have a whole subspace. So it could be a plane. It could be a higher dimensional plane. So given a vector y and a subspace W in Rn, there is a vector which we'll call y hat in W. Such that y minus y hat, so this should look familiar to what we did last time, is orthogonal to W. And y hat is the unique vector in W that's closest to y. Okay, so what does this look like? Let's say W is just this subspace here, the XY plane. So and we have some vector y. This vector in the xy plane, y hat, that you get by projecting y onto W would be y hat. And you can see that the vector that takes us from y hat to y is orthogonal to W. So that's kind of what we're dealing with here. So we're doing the same idea of with the line, except we're in higher dimensions here. So let's talk about how we're going to find this y hat. So we'll let U1 through UN be a basis for Rn. Okay, since we have a basis for Rn, we can express any vector in Rn as a linear combination of these basis vectors. Okay, so nothing new here so far. We have a vector in Rn, and we're saying we could write it as a linear combination of the basis vectors. So the terms in Y can be grouped into two parts. Okay, so that so we could group together some terms of Y so that we could express Y as the sum of two vectors. Basically, the idea here is we're going to write it as the sum of this vector Y hat plus the other vector. That's what we're trying to build up to now. Okay, so I'll give you a second to write this down. We're kind of like in the middle of a thought, but there's a lot of writing here. I guess before you do that, so where Z1 is a linear combination of some of the basis vectors, and U2 is a linear combination So Z1 is a linear combination of some of the UI, and Z2 is a linear combination of the rest. Okay, so the big idea here, again, I know it seems like a lot, but the idea here is we're going to take a vector y, we're going to try to write it as a sum of some vector in our subspace plus a vector orthogonal to the subspace. Okay, in this technique here, we'll get to an example in like one. I have one more sentence, and then we'll get to an example. This technique that we're doing here, writing our vector as a sum of some terms, we're going to break up our basis into two separate parts. This will be useful when our basis is an orthogonal basis. I mean, ideally, we have an orthonormal basis, but orthogonal is good enough. So this technique, and we'll get to an example, I promise. Okay, so let's take a look at an example to kind of see what we're doing here. All right, let U1 through U5 be an orthogonal basis for R5. Okay, and we'll write some vector as a linear combination of the basis vectors. So we'll let y equal C1U1 plus C2U2 plus C3U3 plus C4U4 plus C5U5. We'll let W be the span of U1 and U2. So the question is, write Y as the sum of vectors So write y as the sum of a vector z1 in W and z2 in W perpendicular. Okay, so we have some orthogonal basis. and we want to, and we also have some subspace that is the span of U1 and U2. What we want to do is express Y as the sum of two vectors. One lives in this span, one lives outside of this, outside of W. And then we got to show that, in fact, the second vector is orthogonal to the first vector. Okay, so I'll just kind of walk through this because it's our first example. So Y is equal to C1U1 plus C2U2 So Y is equal to this linear combination, right? That was given to us. We want to write Y as the sum of vectors Z1 in W. So let's take the terms that live in the span of U1 and U2. So these terms live in the span of U1 and U2. These terms do not. So we'll take this to be Z1. And everything else is Z2. Okay, so clearly Z1 lives in W, right? W is the span of U1 and U2, and Z1 is just some linear combination of U1 and U2. So how do we know that Z2 is in W perpendicular? How can we check that Z2 is in W perpendicular? I guess if you don't know how to answer that, another question for you is, what exactly is W perpendicular? And it's okay if you don't know. I would just like a little bit of feedback. Vectors must be orthogonal to those in W. Yeah, exactly. So any vector in W, and I guess it is also hard to type out these answers. So I understand that. So how do we show that? How do we show that W2 is in? I mean that Z2 is in W perpendicular. Let's just show that Z2 is orthogonal to the basis vectors of W, and then it's going to be orthogonal to any linear combination of the basis vectors. Right, so if we show that this vector is orthogonal to both of the basis vectors of W, then it's going to be orthogonal to anything in W. So let's do this dot product. Z2 dotted with U1. Well, that's Z2 is C3U3 plus C4U4 plus C5U5. And now we want to show that this is equal to 0. Well, we have properties of the dot product that say we could distribute it into a summation. So this is equal to, I'm probably going to need more space, so I'll just erase all this. Right, and so my question to you is, what is U3.U1? And what is U4.U1? And what is U5.U1? Well, these are all 0 because our basis is orthogonal. So if we take the dot product of two basis vectors, then it's going to be 0 since we have an orthogonal basis. Right, so this is equal to 0. So Z2.U1 is equal to 0. And you could imagine a very similar calculation could happen to show Z2.U2 is equal to 0. Right, you just switch all the U1s with U2s and it would work out exactly the same. So Z2 is orthogonal to both of the basis vectors of W, so it's orthogonal to W. So our choice of Z2 is correct. We could write Y as, so Z1 is equal to C1U1 plus C2U2, and Z2 was equal to C3U3 plus C4U4 plus C5U5, and Y is equal to Z1 plus Z2. Okay, so this is kind of the main idea that we'll be looking at for the rest of this week, is we could take a vector, we could write it as the sum of two vectors. This is just like we did with the line, except in higher dimensions now. We could write it as the sum of two vectors, one that lives in the subspace, one that lives perpendicular to the in the subspace that's perpendicular to W. Okay, so this seems like a good place to stop. I'll stay around and answer any questions you may have. Remember to hit the like button before you leave. That's very important. But yeah, we'll just pick up with this tomorrow. This was kind of just the intro. Tomorrow we'll get to more examples. Are you going to post test solutions before the final exam? Yeah, I plan on posting them like probably today. All right, well, I'm out of here. If anybody wants to, if they need to talk for any reason, send me an email and we could Zoom. Yeah, I'm available like all the time. So just if you want to chat, shoot me an email and we can chat about whatever you want to chat about. Bye-bye.